Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, I'm going to be talking about something that I think is really cool and really exciting. I do have the privilege on this channel of working on some really cool things, but this was something that was donated that kind of blew my mind at how cool it is and how inexpensive it is. It allows you to do some really fun things with our favorite 8-bit computers that I haven't seen before. And because of that, it makes me so happy to share this with everyone, and I can't wait to do that. So without further ado, let's get right to it. All right, we have a package from Michael at BitFixer in Daly City, California. That is a city just south of San Francisco, so hi to all my Bay Area viewers. There is a note in here and a couple packages that are taped in so they don't go flying around. Let me cut these out of here. I'm going to dive straight into what's in these packages here. So this is, I'm not quite sure. It's like a 40-pin dip socket. Ooh, that's unfortunately got some bent pins. Oh, you know what though? He purposely installed that. Hey, that's pretty smart. This is just a 40-pin dip socket that he installed over the pins that are on this PCB, kind of as like a sacrificial anode on a boat where it absorbs the corrosion. Well, in this case, this absorbed the beating of being shipped. So yeah, some of the pins are bent or broken off on the socket, but if I pull that off, then what will be underneath there will be nice straight pins. But anyway, I'm really curious what this thing is. So on the bottom of the PCB are 40 pins that go into like a dip socket. Then there's a PCB that's got, of course, a socket on the top here. And then it has a second socket on the top here. And inside that is a little PCB that's got like probably a CPLD or a mini FPGA or something, a couple of voltage regulators. It's got some dip switches, some other ICs on there. So that's curious. And let's look at what's inside this other little bag here. And then in here is something that's got a little ribbon cable and like a pin header here. Okay, I don't quite know what this stuff is. Let's see what he says in his letter. All right, his letter says, I've recently came across your channel and I've been enjoying it a lot. Your repair videos have inspired me to dust off the oscilloscope and try to fix a few machines I've been hanging onto in my garage for a while. I have a couple Apple IIIs and a few Commodore machines that definitely need help. I wanted to send you a gadget which may be of use to you in the future. This is a ROMulator, a recent project of mine which is a programmable RAM and ROM replacement board and debug console for 6502 based computers. It was built specifically for the Commodore PET and has several ROM sets and memory configurations for PET models built in, but it can also be used with pretty much any 6502 computers with different ROM images and memory maps. Programming and debugging of the device uses a Raspberry Pi. This is plugged into the Pi header. Got it. Using a small adapter board I've included. With the debug functionality, you can halt a running CPU and get a full readout of the contents of ROMulator's memory. Having this will make finding ROM and RAM faults easier during repair. More information and instructions on how to connect a Pi device for programming and debug are on my GitHub, and he has a URL, which of course I'll include in the description below, or at my website, bitfixer.com. Whenever you get the occasion to mess with it, there may be some updated firmware available, so you may want to check for updates. Also, please feel free to contact me for help with the device or if you have any questions. Thanks for the great videos and hope the ROMulator proves useful to you, Mike. Wow, this is so darn cool. I know there are 6502 ROM RAM replacements for the PET specifically already out there. In fact, if you can believe it, I actually have one that I sort of half built up. I have the PCBs manufactured and it's got a bunch of surface mount components, and I just never got around to building it up because luckily my PETs are working right now. I haven't had to troubleshoot them. But something that is more flexible that can work in other 6502 machines as well, that is incredible. And none of the ones I've seen have a way to debug and halt the machine using a Raspberry Pi. Like, that's just really, really cool. I can't wait to check this out. Let's take a closer look at the ROMulator. So this is the main board, and you'll see it's made up of two parts.
On this top board here, this plug-in module is a small FPGA, a couple voltage regulators, and a pin header. And it connects to this lower board, which is a very simple affair. On the bottom of it, there are pin headers. This is what plugs into the motherboard of the computer you're going to be working on, say Commodore PET, something like that. And then there's a socket here, and that's for the CPU. So this board plugs into where the CPU is on the motherboard, and you take the CPU and plug it in here. You'll see those surface mount ICs there. Those are level shifters to convert between the 5-volt TTL logic that the 6502 uses to the 3.3 volts that this FPGA uses for its I/O lines. And then you have a bank of dip switches there, and that allows you to configure the different profiles that this uses for the ROM-RAM replacement. And I'll talk about that more in a second. And on this little board here, this is a little tiny Pi hat that plugs into a Raspberry Pi, which you have to supply yourself. This is a Pi 3, and this plugs into the board like so. And then this little extension header plugs into this board, and that allows you to do all the debugging and the configuration of this thing. The hat plugs into the Pi like this, hanging off the edge, which is good because this Pi 3, for instance, normally has this case on here, and if the little hat went this direction, it actually wouldn't fit because this plastic case only has an opening here for a cable. The ROMulator does not require a Raspberry Pi for normal operation. Basically, for programming and debugging, you do need a Pi, but otherwise, you can run this with this disconnected. This is Mike's website, bitfixer.com. This is where he sells the ROMulator, and he charges just $30 for an assembled unit. Now keep in mind, this is an open source project, so anyone could build this, but notice here the very small surface mount IC means that putting this thing together is probably outside the wheelhouse of most people. Now let's check out what he writes for the description here. It's a RAM, ROM replacement and diagnostic board for the PET, Apple II, and other 6502-based microcomputers. The ROMulator connects to the 6502 socket in your computer, and the ROMs to use are selected by the dip switches on the board. It allows you to view the memory of a running 6502 machine using the replacement RAM by halting the CPU and sending the memory contents over SPI to the Raspberry Pi. That happens through this pin header here. The ROMulator is open source, and the schematics and Verilog code for the FPGA are available here on this GitHub repo. So here it is. This is all the various code and instructions on how to do the installation of it, some of the basic configuration. This is what comes in the unit, sort of set up for pets. And it talks about the programming and the debugging, and if you don't have the Pi hat, how to hook it up yourself. You can just wire it up directly. Installation instructions, programming instructions, and some even custom firmware stuff. And as he mentioned, all the Verilog code and the source code and the schematics are all up here. If you don't want to buy the ROMulator from Mike directly for a really reasonable price of $30, you can go ahead and make it yourself. I know I haven't even showed this thing working yet, but I am very excited about it. And one thing that is so cool to me is that he's only charging $30 for this thing. There are other ROM RAM replacements like this one here at the Future Was 8-bit. This thing is 70 pounds, but the difference between this PET ROM RAM replacement for 70 pounds versus Mike's ROMulator is the ROMulator uses an FPGA, which means it's fully configurable from the Raspberry Pi, so you can change what it does. All the existing ROM RAM replacements that I'm aware of, like this one here at the Future Was 8-bit, it's hard-coded to only support the PET. The ROMs are already loaded into the thing, and it has configurations for the mapping, the memory maps of how the ROMs are loaded in and out of the system, and also the RAM is loaded in and out and configured with the dip switches. This is all hard-coded. It is not configurable. So this device here, while it's cool, only works on the PET, which, okay, you know, if that's what you need it for, is fine. But the great thing about the ROMulator is it can replicate everything that this thing does, but also work on other 8-bit systems. Now, Mike alludes to that in his page where he says it works on the Apple II and other 6502 systems. So let's do some testing on another 6502-based system to see this in operation, but also to see some of the capabilities of what this can do that none of the existing ROM-RAM replacements could even hope to do. So I'm going to be testing out the ROMulator on this VIC-20, and we're going to be able to do some pretty cool things on here that I don't think are possible with any of the other ROM-RAM replacements that exist right now. So let's turn on this machine, make sure that we have a working VIC-20. And there we go, a working bone stock VIC-20. This was the machine that I had to replace these two bus transceivers on because they had corroded away. They were the MOS parts. This thing has soldered everything except for the CPU and the bus transceivers which is perfect because that allows me to plug this in. The only thing you have to take into consideration with the ROMulator is the orientation of the CPU. Like there's stuff next to the CPU here, and if I had to put this way, I would have to put a bunch of sockets on here to raise this up to clear this inductor here, or whatever this is. But luckily from an orientation perspective, you can see there's a notch right here, and that goes onto the board like this. So let me pop out the CPU, and we'll plug the ROMulator into the board. Well, actually first, let's put the CPU into the ROMulator. Make sure you have the orientation of the chip correct, the notch is there. And then we just push this into the board, like that. I've already used this Raspberry Pi to pre-configure this for the VIC-20. So currently I have it all set to 0 on the dip switches, which when I turn this on, the machine should work and it should be like a stock VIC-20. There is a little LED that flashes underneath the ROMulator there, and there we have it. The VIC-20 is up and running. Oh, let me get a keyboard so we can do some typing on the VIC-20. This is the one from the ZIF-64, which I'll just leave off to the side. Okay, there we go. So there we go. Oops, I had the shift lock on. So a working, completely stock VIC-20. In case you're not familiar with the VIC-20, this machine has just 5K of built-in memory, but it does support RAM expansions plugged into the cartridge slot. And I've covered those before. As a kid growing up, I actually had a VIC-20. It was my first computer, and I had the 16K RAM expansion slot. So it was 16K here, plus the 5K on the motherboard. So that gives you 21K total, and in BASIC, it's 17,000 bytes or whatever, something like that. Let's take a look at this article here, which talks about the memory layout of the VIC-20. This picture is actually a really good representation. So you have various colors here showing what sits in the full memory map of the 6502, which remember is from 0000 to FFFF, which is 64K. The red sections here are the onboard RAM. So that's it. That's all you have. You have a little pit at the very bottom from 0000 to 03FF, and then you have a small bit from 1000 to 1FFFF. All of this blue stuff here is available for expansion. So when you plug a cartridge into the cartridge slot with RAM, it's going to be adding memory into one of these areas, one or more of these areas. They're labeled as block 1, 2, 3, and 5. And then there's a little section right down here, which is RAM 1, 2, and 3. This little section here is 3K of memory, and I think Commodore sold a 3K RAM expansion that went in this space. But the 16K RAM expansion that I had as a kid, I think probably used block 1 and 2. And there are some RAM expansions that can use up all of these blocks. It fills in all these gaps here to give the computer a total of 40K of memory. And that's this onboard RAM plus all of these blue boxes adds up to 40K. When you plug in a game cartridge with a ROM in it, it sits in this block 5 here. This is where the ROM code goes, and it can take other space as well. And that auto starts that ROM. So when you have a game cartridge here, when you turn on the computer, the kernel takes a look in this A000 block, and if it sees the right signature or whatever it is, it will just start that ROM automatically. The way that these ROM RAM replacements work is they actually sit between the CPU and the motherboard, as you can see. They physically sit there, and they have the ability to intercept the data and the address lines from the CPU to the motherboard. So if the motherboard is trying to read something from the VIC-20 block 1, well, normally there's no RAM there, right? Because I don't have a cartridge plugged in. What the ROMulator can do is it can act as RAM. So when the CPU goes to read address 2000, instead of coming back with nothing, which it would if it just talked to the computer, this thing would have RAM, and it would present RAM back to it. It can also replace the RAM that's actually on the motherboard, which is this SRAM right here. So if it goes to read from this SRAM, you can configure this to actually intercept that read and go to the internal RAM that's on this board as opposed to what's on the motherboard. That's really useful if the RAM is bad or some other component along with the RAM is bad and you want to test the machine to see if it's working. This is especially useful on the PET because it's got a lot of ICs on there, and if one of them fails, the whole computer doesn't work. But you can use the existing ROM RAM replacements, like the one from the Future Was 8-bit, or this one to replace all of the onboard memory and all of the onboard ROMs, which just allow you to diagnose the entire system. And on the PET, if you're stuck with an old version of the ROM, like ROM version 1, like on my original PET 2001, you can run ROM 4 or BASIC 4 using these things because it just intercepts all the calls to the onboard ROM and replaces it with a newer version. As I had mentioned, all those other replacement products have the ROMs and the configurations all hard-coded into the device, while this one with the Raspberry Pi allows you to completely configure and load any ROMs you want onto it. So with something like this on the VIC-20, we could use this to not only replace the ROM and the RAM that's on this board, but I could fill in all of the gaps of the RAM that would normally be taken up by a cartridge. And also, what about switching the ROM to something else? The basic ROM or the kernel ROM, we could load something else in. And that's all with the original chips still on the board, still soldered in there, not even removed. There's one small caveat to replacing the RAM, which is right here on the VIC-20. The VIC chip, which is this chip right here, it stores what's on screen in the system memory. So if the CPU writes to a specific location in the onboard RAM, then that gets immediately displayed on the screen. So if we replace all the onboard RAM with RAM on the ROMulator, then you won't get any screen updates. Anytime the CPU goes to write to the screen RAM, you'll just see garbage because it'll be whatever's in those chips. The VIC chip is physically connected to these chips, so it's always going to be getting its display contents from these onboard chips. I'll show this a little more in a second when I show how the configurations work on this thing, but it supports a couple different modes. One is the ROM replacement, so that replaces these read-only memories here. Another is RAM replacement, where it just completely replaces the RAM on the board or it takes over for RAM that's not even there. And another is a write-through mode, which means that it replaces the RAM with what's in here, what's in this FPGA, but it also allows the CPU to write to the memory that's on the computer. That's especially helpful on a machine like this because the CPU needs to be able to update the contents of these chips so it would display properly. But imagine there's a fault with these chips. There's a little bit of bad memory in there. That could prevent the computer from working entirely. So in that write-through mode, the CPU is writing to both the memory on the FPGA and on the motherboard, so you should be able to see what's on the screen, but in case this memory is bad, the CPU reads only from the memory in the FPGA, so it should not crash, and this bad memory should not affect anything. So I've pre-configured some configurations on here, with zeros being just a completely stock machine where everything on the motherboard is used normally. But if I switch this to 1, so we flip that switch up, when I turn on the machine, we now have a nearly stock machine, but there's a little bit extra memory. Notice 66,055 bytes free. That's because I told the ROMulator to fill in the RAM gap right here between the two onboard memory chunks. So RAM 123. So we have an extra 3K of RAM, giving us 6555 bytes. So it's completely configurable that way, which is so cool. But let's just completely max out this machine. So I'm going to flip this switch. I think this is set to 5 now, profile number 5. And I'm going to replace all the RAM on this machine with what's in the FPGA, and I'm going to fill in all the gaps as well, which should completely max out the RAM capability of the VIC-20. In addition, I'm going to swap out the kernel ROM with Jiffy DOS. And this is all happening just with this thing here. Nothing else is connected, as you can see. And let's turn on the machine. Let's see if this works. I was doing this late last night. Hopefully I didn't make a mistake. And there we go. Look at that. 28,159 bytes and Jiffy DOS, copyright 1989. Even if you only use the ROMulator for this one capability, the fact that this $30 device has now maxed out my VIC-20, it's that alone is a good deal. But let's keep going. And I want to show you some of the amazing things that you can still do with this. So I need to plug the Raspberry Pi SPI cable into this. And yes, I'm going to do it while it's turned on. There we go. It did freeze the computer, so maybe I should have turned it off. But we're now up and running again. Okay, so I'm going to write a little program on the VIC-20 here. Print, let's see here, Adrian Black. I'll just put my name. And we'll do 20, go to 10. And I'll run that. There it is, Adrian Black. Everything is working normally on the VIC-20. Here's an SSH session open to the Raspberry Pi 3. And I think you could use any Raspberry Pi. I just happen to have a 3 sitting there. That's what I used. I'm going to run this command bin console-r, and I'm going to output that into vic20.ram. And what this is going to do when I hit enter is it's going to take the entire contents of the RAM that's in the FPGA, which remember in the configuration I have right now is everything. It is doing write through to the system memory for the screen display, but that's it. Everything else is actually in the FPGA. I'm going to run this, and as it runs, the cursor stopped blinking for a split second. And let's use the program hexcurse, and let's look at the RAM we just copied from the FPGA. This is the actual memory from the VIC-20, all 65K of it. Now, if we keep scrolling down, here's the screen memory right here. This starts at 1000. When you have expansion memory, the screen memory moves around a little bit on the VIC-20. It's kind of one of the idiosyncrasies of the machine, but this is that mirrored screen memory. Now, right here, you see it says Adrian Black on the text mode. This is the actual basic program that is stored in memory, and this is being stored in the FPGA RAM, not on the motherboard at all. I'm going to type in here, hello kitty, like that. and I'm going to save this. Let's Control Q out of here, save the file. Let's put this back into the FPGA RAM right here with this command. And when I do that, the cursor stopped blinking for a second. Oh, okay. Well, this happens occasionally, and the VIC-20 looks like it's actually frozen. So let's power cycle the computer again entirely. I've noticed this happens with the VIC-20. It probably doesn't appreciate the CPU just halting. And I think if this is a 65C02, it would work a little bit better. That CPU has the ability to halt without crashing things. We'll update the RAM again, just like we did. And on the computer, if we type list, there's the program, Hello Kitty. In fact, you notice I turned the computer off and then back on again. And let's do it one more time just to show you that that actually works. So there it is. If I type list, oops, list, we have nothing in memory, right? And let's update the RAM again. It didn't even reset that time. And if we type list now, there's the program loaded directly into the VIC-20. So there it is, Hello Kitty. And let's just do that same process again. Let's load the RAM again. So this is the current copy of the memory. And we'll do hex curse. And we'll change the program to be something else from Hello Kitty. Let's change it to bad, oops, I don't know about typing lowercase. Bad kitty. There we go. Control Q, save, enter. Let's write this back into the memory. And the computer froze again. You know, when I was testing last night, this was working a lot more reliably without so much crashing. But of course, like, because it's a state, like it's a save state, so to speak, for the whole thing, you can just do that again. And now when I type list, bad kitty, there it is. So it totally works. So there's more that we can do. We can edit the entire memory of the entire computer, but that includes the ROM space as well, not just the RAM space. So here we are looking at the basic ROM on this machine. And here's the ready prompt, for instance. Let's change ready prompt to kitty. Okay. And let's change OK to no. I keep typing in lowercase. And let's save this. Do you want to save? Yes. And let's load this back into the VIC-20. And it didn't crash that time. So we're still working. And we'll type list. And instead of ready, it now says kitty. So let's say run, and you hit stop, break in 10, kitty. So we're actually altering the contents of what's in the ROM in this machine from the Raspberry Pi. Now with the cable connected from the Pi to the FPGA, I think it keeps the FPGA powered up across resets. So let's see if we power cycle the machine. Will that kitty stay in there instead of, yes it is, there it is. I power cycled it and it says kitty now. When the machine boots up, it clears the system memory, so my basic program is gone. But it doesn't clear the ROMs, and those stay in the RAM of this powered up FPGA. So if we altered the kernel to not clear the RAM at power up, our basic program would have probably survived as well. So let's go down to E1000 hex, and that'll be, let's see here, that's the kernel ROM. And here is the Jiffy DOS banner here. So let's just edit this, and it's hex, oh, let's see. And put Adrian Black 2021 like so, and we'll quit out of this. You want to save changes? Yes. And we're going to push the RAM ROM back into the machine. It didn't crash or anything, it's still running, but let's just power cycle the VIC-20 entirely. And that should have altered the banner. EEVBlog 2021. Kitty. Hi, Kitty. So typing run, we don't have the program that's loaded in there, but of course we can just push the entire contents back in, and their bad kitty is now loaded into BASIC. Oops, there it is. So I think this is a good demonstration of how incredibly powerful this thing is, not just for diagnosing computers if you have ROM and RAM failures on the board, but also upgrading a computer on the fly like I've done with this, and then also the debugging capabilities. The only thing this thing doesn't do that I wish it had a flag to do is that when you upload the RAM from this back into the FPGA, if you have any banks configured for write-through, like I have the screen memory configured, it doesn't update the RAM that's on here. So I can't use that hex editor to edit the screen memory and have it actually show on the screen. It will change the contents of what's in the FPGA, but it won't change the contents of what's on the motherboard. So for a save state, there's no way for me to get back to exactly where I was in a game because the contents of the onboard memory would never be updated. I have one more thing configured on here I just want to show you, and it is profile 6. Now, while this is connected to the Raspberry Pi, switching the dip switches doesn't actually change the configuration of the FPGA. It must load that configuration when you boot the thing up. But I have found that simply writing the configuration back into the FPGA of like the memory banking seems to reset it and then load the dip switches. And to just quickly update it, you do make program, and that's going to reload all the code in the FPGA. Now it does freeze and actually will end up crashing the machine because it's clearing out the entire memory that's in there. So yeah, don't do it while the system is running like I just did it. But if we power cycle the computer now, this is one of the other things that you could do with this, at least with the VIC-20. And here it is. The VIC-20 diagnostics is currently running. Now this is actually a cartridge ROM that normally would be plugged into the cartridge slot. Because we can load RAM or ROM into any of these banks, this block 5 right here is actually where cartridges normally exist on the VIC-20. And this little diagnostic ROM sits in this space. So I altered the config file for this profile 6 to, instead of making this RAM in block 5, to just load that 4K diagnostic ROM cartridge into it. And when you power on the VIC-20, it auto starts whatever's in block 5. And there you go, you saw that the diagnostic ROM came up. It is flashing here that the serial bus is bad, and that's because I really do need to have a loopback connector connected to that connector to make this work. And there are plans online if you want to make your own VIC-20 diag harness. I don't happen to have one. Even with that ROM loaded now, I can still read out the contents of everything, including that ROM, and we can hex edit, and we can change that ROM while it's loaded in there. Let's see, it should be in A. Here it is. So this is the diagnostic ROM, and there's the cycle count. Let's do a little hex editing here, and we'll change RAM test to Adrian with 2 exclamation points. So we'll save out of this. We'll write this back into the system, and then I'll power cycle it. And now that diagnostic ROM, when it pops up, Adrian, instead of RAM test, it says Adrian. I don't know, there's something really just crazy cool about doing this stuff. On a running system, we can alter what the code says. And honestly, you can actually do it on a system that's running. Let's see if I can get it quickly enough. I'm also going to change where it said Adrian, which was originally RAM test, I think. I'll put it to Apple RAM. And what we're going to do is I'm going to change this in between cycles of the RAM test, and let's see if this works. So I'm not going to write this yet. Let's power on the machine, and we're going to change this. I'm going to try to get this in between the test. Okay, Adrian 1, and I did this, and there, it changed it to Apple RAM. So the second pass, it would have said Adrian twice, literally changed it while the system was running a RAM diagnostic. That just shows that this really is working on a running machine. I don't know, I'm finding this amazing. Just the combination of a Raspberry Pi with the VIC-20 and altering RAM on running hardware is just so cool. You could do all of this with Vice. You could do all of this in emulator. You can break it, you can look at what's executing. I mean, the diagnostic capabilities of running an emulator are amazing. To be able to do it on real hardware, that's just like next level. Lastly, I just want to take a look at how you configure the ROMulator from the Raspberry Pi. And this is all talked about in the GitHub repo, but I just figured it out. And if you want to do this stuff yourself on the VIC-20, you can use my configs. So in the tools here, there are 2 files. One is called memory set, and it's this VIC-20 one here. And what this is this is specifying all of the different ROMs that are used. That's all that's in here, is pointing to what ROMs you have. So remember on Profile 6, which is the one I'm running right now, we have the regular stock, basic, and kernel loaded, and you type in the memory location, so C000 for basic, and E000 for kernel, and then the diagnostic ROM VIC-20 is loaded into A000. Now I could load any game ROM into here as long as it didn't have a weird header on it, like it was exactly 4 or 8K, would fit in that block. And then right here you see Profile 5, I replaced the kernel ROM with the Jiffy DOS kernel, and that's how you load the various kernels. I'm not sure I needed these lines for 0 on the basic and kernel, because in that profile, it's not even using any of the ROM replacement. It's just completely in pass-through mode. It was more a test to make sure that the computer was still running with this board not doing anything. And then the other file that you need to worry about is the enable table, and I have one here for the VIC-20. And this is what configures all the various modes of the memory. So here is profile 0, and this is set to take the entire address space and have it in pass-through mode, 0 through FFFF. And then I created some more as I was testing this. This is profile 1, which I showed earlier on this video, where I only add the RAM to that little bit of space in between the two onboard memory chunks. So everything is passing through to what's on the motherboard, everything, ROMs and RAMs, but this board is creating new RAM in that little bit of space, that 3K of space from 400 to FFFF. If we scroll all the way down to profile 5 here, so for the first little bit of memory, I have it in write-through mode. And actually, I didn't need to do that. I could have just had it in the read-write mode to replace it completely. Then I have that extra 3K of RAM that I've added. And then we have the screen memory, which is in write-through mode. And that's that from 1000 to 11FF. That's the exact little chunk of memory that's used for the screen. Everything after that, like 1200 to 1FFFF, which is onboard memory, is in read-write mode. And that means it's being replaced entirely with what's on the FPGA. And then from 2000 to 7FFF, we have read-write, and that is creating brand new RAM that would normally be in a cartridge. So that doesn't exist at all on this machine. We have 8000 all the way through to 9FFF, and I have that in pass-through mode, and that's because on the VIC-20, that's the color RAM, that's the I/O space, like for addressing chips and stuff. It is needed for operation of the machine. I think there's a little bit of that you can actually replace in write-through mode with RAM. There's a way to do that to get a little extra RAM in some of this space. I think it's in the 9000 area. You put it in write-through, which means the CPU can write to registers to control things, but whenever it reads back, it would actually read back from the RAM on here. So it would write to the register and to the RAM. I think that's possible on the VIC-20, but that's very dependent on the architecture. And then we have this block, which is A1000 through BFFF. That's another 8K, and that's the cartridge ROM or RAM, depending on what you have plugged in here. And then we have the two onboard ROMs, which is C1000 and E1000. So that's the basic ROM for C1000, and E1000 is the kernel ROM. Now, even though it's set to read only, which is specifically saying this is a ROM and it loads it from that other file where I had the ROM specified, it doesn't mean I can't write to it with the debugger tools on here. The computer can't write to it. Like if you try to use an assembler on here to write to those locations, it won't work. It is possible, I'm not totally sure, if I set this to read-write, that instead of being RAM, it actually loads that ROM into that space, the one specified in the other file, and then the VIC-20 itself could write to that memory location. I haven't tested that, but that might be possible. And then profile 6, I have A1000 through AFFF, that's 4K, and that is that diagnostic ROM that loads from that file. So that's basically it. You can create your own custom maps here for whichever machine you're using. So if it's an Apple II or a BBC Micro or a PET, you can completely configure as many as you want, up to 16 profiles here with various things banked in and out, going through the motherboard, going through to this only, going through the files, all sorts of stuff. If you create a memory set and an enable table, you do need to edit the make file, and you need to specify up at the top here which two files you're going to be pulling from. It's set to some like default file originally, and then the enable table is like for the PET. That's the way this came out of the box. So you just have to edit these two things. And like I said, you do make program, and that will compile or do whatever it does to create the firmware for this thing that loads all those configurations in. If you change either of those files, you do need to do a make clean first, and then you can do a make program, and that loads it up. There is a ROMs directory here, and this is where you put the ROM files that the memory set file pulls from. So there were no paths specified in there. You just load all the ROM files you want into here. So I could load game cartridges into here, and I could specifically program the ROMulator with game cartridges, and that would work. Or I could just create it as RAM, and then I could load the game cartridges in the VIC-20 off of a disk into that memory location, A000. I could also use the debugging tools on here to load a game cartridge into that 64K memory map. I just have to put it in the correct spot and then copy it back in the ROMulator, power cycle the VIC-20 or reset it, and it would launch the game. I also noticed a file that Mike had in here called nop.bin or noop. And I have a feeling if we hex curse this, what this is it's an entire memory that's loaded with no-op instructions for the 6502, and it's EA. I've had videos on making your own no-op generator, and you do that by disconnecting the data bus from the CPU to the machine, and you hardwire that EA instruction or opcode. So as the processor runs, all it ever sees is EA, which has that same effect of running through the entire address space and exercising the chip select logic for every single device on the motherboard. Well, this can do it without any kind of hard wiring or whatever. You just load that as one of the configuration profiles in the ROMulator, you set up no-op, and there you go, you're off to the races. That would be incredibly useful in things even like a 1541 disk drive, where you have no real way to see what's going on with the machine, and you have to use an oscilloscope or a logic probe to test the chip select logic. So I think you might be able to tell that I absolutely love the ROMulator. What a cool thing it is. The fact that it's open source, the fact that it's only $30 if you buy it from Mike, there's just so many incredible things about it. And hopefully I can get some attention on the project. Maybe people can enhance the capabilities of it to, for instance, write that memory into this onboard memory so you have true save states with your 6502 machines. Check out the GitHub repo if you want to see more about how to use this and get set up with this on your Raspberry Pi. There was a little bit of information that was missing, like how to configure those enable tables, but just checking around through the files and looking at the source code for some of the programs made it very simple to figure out how that should actually work. I'll of course put links in the description to both the GitHub repo and Mike's store so you can buy one of these yourself. And I do have to apologize to Mike. He sent this to me sometime back in 2020, and I started to play around with it, then I didn't have enough time, so it sat on my bench here in this pile of chips and stuff for the longest time. But I finally got to it, and this thing deserves some attention because it is a really, really cool project. So that's going to be it for this video. If you enjoyed it, I'd appreciate a thumbs up. And if you didn't, you know what to do, and put a comment in the comment section below and subscribe, that would be great. Don't forget to check out my second channel, which of course has lots of cool videos on it lately. I'm just getting off the ground there, but I'm putting shorter, more fun videos on there, and not just candy reviews, by the way. I actually haven't done a candy review. There'll be one of those coming soon, but there's other neat stuff there. And of course, thanks very much to my patrons. Their names are scrolling up the side here, and thanks Mike for sending this in. I really appreciate that. And that's going to be it. Stay healthy, stay safe, and I'll see you next time. Bye-bye.